We are from group 19. Our project is greenhouse 2.0. So what is 2.0 in order to address this problem domain for greenhouses which are designed to control, provide a controlled environment for plant growth. However, external factors such as temperature and fluctuations can make it difficult to maintain this condition. This can lead to like many problems such as reduced plant growth, increased risk of disease, over yields, and higher cost. As you can see, for tomato, it needs different types of temperature and weather conditions and environmental conditions throughout its growing phase. It's same for the different plants, and the conditions might be different. So our greenhouse has to provide those conditions. So these are the graphs that were generated from the data that we acquired. As you can see, the internal temperature of the greenhouse fluctuates a lot when compared to the external temperature. This is same for the hourly data of temperature as well. It fluctuates a lot since it's hourly data. So same goes for humidity. It fluctuates a lot, and same goes for humidity hourly data. So in order to solve this problem, first we collected and pre-processed the data and analyzed the data. Then we built and trained our ML model. Then we integrated our controllers with our system using MQTT and our machine learning dashboard. And then we created and deployed the model and dashboard and integrated them. So this is the greenhouse area where we collected the data from the sensors and the plants. So our solution, when we move to solution architecture, our solution architecture is MQTT, which is subscribed to the controllers, and the topics messages that are needed for the topics will be published by the cloud dashboard, which the cloud dashboard takes input data from the weather conditions of greenhouse, and which is automatically controllers. So in terms of solving this problem, in terms of machine learning, we used supervised learning first to find the initial patterns, and then we used hierarchical algorithm and clustering algorithms to find out the different type of clusters throughout our data, and our machine has to adapt to our data and weather condition throughout the year. So when we tried to solve this problem, we were faced a lot of issues. Those problems are like we didn't have no pre-data set. So even when we fetched the data fetching the data was very slow. So we used multi-threading to improve the data collection speed. And in terms of we got some wrong weather details in different trials of data in the greenhouse, and we didn't get proper accuracy because of the wrong trials. So in terms of technology, we used Python to build our machine learning models. To build our API, we used Flask, and we created a Docker image to host that Flask application, and the Docker image was stored in Amazon ECR. In order to run this Docker image, we used Kubernetes with Amazon EC2, and we used MQTT through port 883 to make it more secure, and we used 443 to expose it to the internet with HTTPS. So in terms of testing, we use unit testing, regression testing, and integration testing, and widget testing of the dashboard, which will be used by the admins all the time. Fetch the data. We used agriculture's department's API to fetch the data, but at first when we tried to fetch the API data, it was very slow. So we used multi-threading to fetch data parallelly for different trials, and we merged the data. Like it was comparatively very faster when compared with fetching data in one thread. So we did the same pre-processing thing, such as removing null values, mean imputations, and we dropped all the duplicate values. And then what we did was we created some data frame with average temperature and average humidity values and the sensor readings. And then we got the external temperature from the API and some data that we had from the agriculture sensor. Then we merged all those data set, and then we tried to run the data set through machine learning model, such as basic linear regression. The accuracy was 25%. It was very low. Then we tried with different types of model. When we tried with relation tree classifier, the accuracy was 36%. When we tried with lasso model, the accuracy was 21%. When we tried with rich model, the accuracy was 21%. And even when we tried with MLP, the score was bad. Same for the CNN and everything. So we were wondering what was wrong, and then we tried with trial 6 data. So we did the same exact procedure again, and we plotted the graphs for the temperature and humidity variations. And when we did the same procedure again, we were, even for the normal linear regression, we were able to get 90% accuracy for training. And we were wondering what happened. This is because the data in the initial trials were wrong, and the external temperature and humidity were wrong. That's why these data were like not related, not related. That's why the accuracy was bad. And then so we did CNN as well as some complex thing when compared to the decision tree. When we run through CNN, we got 99% accuracy, and we plotted some scatter plot for predicted versus actual values, in order to make sure our values are predicted correctly, and we plotted histogram of residuals as well. And then what we did was we stepped into unsupervised learning to find out what type of clusters we can find out from the data that we got. And we used hierarchical clustering to find some patterns, and we used PCA also to find some patterns throughout our how many clusters that we can generate. So in terms of here we did 3 clusters. As you can see, you can visualize all those 3 clusters, and the box plots correspond to the variables, x variables.
here is the dashboard. Now I am going to compare the two features. For example, feels like and extended temperature. From the image, you can see there is a linear relationship between those two features. And now I am going to change the feature to cloud and compare it with feels like. So now, using the input parameters, I am going to decide whether to switch on the fan or off. So for that, I am going to input external temperature, feels like, pressure, external humidity, and dew points. This will give me the this will predict the internal temperature of the greenhouse. Based on it, we would decide whether to turn on or turn off the fan. As you can see now, the predicted temperature is 32 degrees Celsius. Therefore, the fan will turn on. The turn on command will be sent using the MQTT, and the fan will be turned on inside the greenhouse.